Good morning, everyone. It's 10 a.m., so we will get started. Welcome to today's Research Pays Off webinar. We're glad you joined us today. I have a few NRRA announcements to make, and then we will move into our presentation. I wanted to update on some of the developments from the now postponed May pavement workshop. We are planning for the June team meetings to be extended to 2 hours to facilitate the same team discussions that would have taken place during the workshop meetings. More information will be available later on that. We need to confirm with some of the chairs that will work. We also have 2 webinars already established for to replace the day 1 trainings that would occur. The Geotech webinar is scheduled for Tuesday, May 19th at 9 a.m. Central. This will be also a webinar style with a few presentations, a break, and some Q&A. If you would like more information about that on that webinar, you can email Raul Velasquez here at MnDOT or look for the information to be posted on the workshop webpage later today. We also have an ICT webinar that is tentatively scheduled for Wednesday, May 27th at 10 a.m. This will be the session 3 version, the best practices of AMG milling and pavement from design to construction, which will be a joint presentation. More information will be coming on that as well, so you can watch for all of that and other developing webinars for the information to be posted on the workshop page and announced on our social media pages and in emails. After or just about before we're done with the presentation today, I'm going to be sending a link to a survey. We would greatly appreciate it if you took a few minutes to tell us about your experience and why you chose to join us today and how you heard about us. It should take you about 2 minutes to complete, and it would give us some valuable information as we continue to plan these Research Pays Off. We do have our May Research Pays Off set, the topic and everything. It will be on May 19th. And the topic is developing best practices for the rehabilitation of concrete with hot mix asphalt overlays related to density and reflective cracking. I will have this information posted again later today on the Research Pays Off website, and you should also receive a calendar invitation for that as well later. This is just another reminder to mute your microphones. We will take questions in the text box on the left throughout the presentation and come back to them during the Q&A time. Today we have Dr. Manik Barman joining us to discuss his project, Performance Benefits of Fiber Reinforced Thin Concrete and Pavement and Overlays. And I will share the project page in the text box as well, so you can reference that as you wish. Dr. Barman is an assistant professor in the Department of Civil Engineering at the University of Minnesota Duluth. He has a master's and Ph.D. in civil engineering from the Indian Institute of Technology, Kharagpur, I may have mispronounced that, I apologize, and the University of Pittsburgh, respectively. Before joining UMD, he served as a senior research fellow at the University of Oklahoma for 2.5 years. He also worked as faculty in 2 different Indian universities between 2004 and 2008. He currently teaches infrastructure materials and pavement engineering related courses at UMD. He conducts research on pavement materials, maintenance, and rehabilitation. His current research deals with structural fibers for concrete pavements and overlays, best practices manual for pothole patches, cost effectiveness of pavement cracking sealing methods, low volume road asphalt mixtures, and high density asphalt mixtures. He's actively involved in numerous professional organizations and as a peer reviewer of multiple scholarly journals. He's also the project proposal reviewer for the Southern Plains Transportation Center and the University of Minnesota Duluth, and we welcome him today.
Thank you very much, Lauren. It was a lengthy introduction. I thought you will read selectively. I also would like to thank all the participants today, and also I would like to thank the Minnesota Department of Transportation for inviting me to present the research that we are doing with the Minnesota DOT and with National Road Research Alliance. So, and I hope everybody is doing fine. It's a kind of new kind of life now with this situation. Most of us work from home, also who have kids. So probably you are also guiding them with their schoolwork. That's what actually I'm also doing. All right. So as Lauren introduced, the research project title, it is Performance Benefits of Fiber Reinforced Thin Concrete Pavement and Overlays. The project is funded by National Road Research Alliance. Along with me, I have a couple of undergraduate students working in this project, and also one researcher. I would like to thank all the technical advisory panel members and other experts to help us with suggestions and comments in this project, and also all the data that we get in these projects, all the field data, we get it from Minnesota DOT, our colleague Len, Joseph, Ben, Dave, and many others who collected data and then provided to us. I sincerely appreciate their contribution. Tom Barman is the lead technical liaison for this project. His suggestion and feedbacks are always great, and it definitely increases the research value. So we started this project with three main objectives. So fibers or fiber reinforced concretes are used in concrete overlays, so in not only in Minnesota but different states in this country. Now, in previous projects in different states, we have seen fiber contributes in the performance. So, but we did not, or we were not able to quantify how really they perform, either in terms of reducing the fatigue cracking or how they can help in reducing the faulting. Or if we want to increase the large, or if we want to increase slab size, if fibers can help increasing the slab size. So these are kind of the questions that we had, and with the funding from the NRRA, 8 research test cells were constructed at MnROAD. You can see the picture at the top, there were 2 cells constructed at the MnROAD low volume road track, cell 139 and 239, and there are 6 other cells were constructed in the I-94 westbound. So among the 8 different cells, 1 cell was plain concrete, and the 7 other cells were fiber reinforced concrete. Now these slides shows the cell description. Okay, so out of the 6 cells, out of the 8 cells, first 6 cells are concrete pavement on gravel. So this now in these 6 cells, cells 506, 606, 706 and 806 were constructed on relatively good, strong aggregate base layer, and then the slab sizes were 6 feet by 6 feet. We wanted to construct 5-inch thick cell, but cell 606 unintentionally was constructed with 6-inch concrete. Cell 139, 239 were ultra thin pavement. They were like 3-inch and 4-inch thickness with 6 feet by 6 feet slabs. Cell 705 and 805, they are thin unbonded overlay. They are 5-inch thick, and these two cells were constructed to see if we can increase the slab size by using fibers. So you can see here cell 705 has larger slab size. In the driving lane they were like 14 feet by 12 feet. In the passing lane 12 feet by 12 feet, 13 feet by 12 feet, and 825 had the similar length, but the slabs were narrower, 6 to 8 feet. This is the pavement structure information. Cell 139 and 239, as I said, they were constructed on a little bit of weak base. Here 6-inch class 6 aggregate base was used. 705 and 825, they were unbonded overlay, means like there was a geosynthetic layer was used as a bond breaker. Below that there was 7.5-inch concrete on aggregate base, and then cell 506 through 806 where we varied the fibers doses. One cell was 506 was plain concrete and others were fiber reinforced concrete. Those cells were constructed on relatively thick or strong aggregate base with MnROAD class 5 aggregate base. All those cells were instrumented with different types of sensors. This red one shows here joint opening sensors. Like as we know, slabs contracts or expands with the change of the temperature. In the winter, like slab contracts and the crack width opens, and in the summer exactly opposite thing happens. So these joint opening sensors were installed to track the joint opening or joint movement. We had dynamic strain gauge to collect the strain in the slab because of the wheel load or the vehicle load. Vibrating wire strain gauges were installed to measure the environmental induced strain. Thermocouples or temperature T were installed to measure the temperature at various depths. Alright, now with this information I will move to the distress data what we have got so far. First, fatigue cracking. So the pavements were constructed in 2017 summer and fall. Distress survey was conducted in 2018 in the spring, and in 2019 distress survey was constructed in spring and in fall or in early winter. So for cell 139 and 239 in December, the ESALS were around, for 139 it was 114,000 ESALS. For cell 239 it was 85. The difference between these is because of their thickness, and the other cells were having around 2.4 million ESALS by 2009, and now it should be more. Now cell 139, as we know, the thickness was only 3 inch, and the slabs were constructed on relatively weak base. So we saw cracks really early in the life. Some cracks also occurred during right after the constructions because of the movement of the construction tracks, and which cracks actually continued propagating, and you can see like what kind of shattered slabs shattered in so badly that we can see like pieces of the concrete has formed here. So in September 2018, those slabs which broken or shattered were replaced, 14 slabs. And then when the district survey was conducted in December 2019, after 114,000 ESALS, it was found that more than 75% of the slabs of these cells are cracked. So these are two additional pictures like collected in May 2019 and October 2019. So and there are a lot of cracks in these cells. Cell 239, which had 176 slabs. In cell 139 there are 180 slabs. So in this cell was 4-inch thick and performed significantly better than the cell 139, which was only 3-inch thick. And these are some pictures, like we saw corner cracks, we saw some longitudinal cracks. These are two pictures, one taken in April 2019, another in October 2019. You can see like we some longitudinal cracks now, and then from the district survey we found out that 18% of the slabs have cracked. Cell 506, which was the only cell which didn't have fiber, we had around 96 slabs in these cells. All are 6 feet by 6 feet, and then we saw only one crack in 2018, but we have seen some spalling on the transverse joints, as many as I think 15 locations we found out to have spalling like this. So by October 2019, so there are like a couple of more cracks formed. Still now, until the last survey was conducted, or the data whatever I have, I know there are like 3 cracks in this cell, no other cracks. So 2% slab cracked by 2019 October after 2.4 million ESALS, which is a great, I would say, because this 5-inch thick slabs were actually constructed for the low volume road, and only 2% slab cracked after 2.4 million ESALS, which is really great. But we'll have to keep it in mind. The base layer is really strong, 11 inches of aggregate base. Cell 606 only had one corner cracks, but this corner cracks is on the very first joint, along the very first joint, or it's kind of, you can say it's a transition here. So this is another cell. So this is just the beginning of the cell 606. So so this crack probably has kind of is construction related. So I or Tom also suggested this may not be a typical fatigue related corner crack on the 6 feet by 6 feet panels concrete pavement. So basically we do not have any crack, you can say, in 606. Cell 706 and 806 actually did not show any fatigue crack yet. In cell 806 we saw this kind of tiny little crack, but that's propagated off from the joint opening sensor location. So these two cracks are also not fatigue related. Cell 705 and 805, these are a thin concrete overlay, unbonded overlay. So and then, as I told before, then we varied the slab size. Basically the width of the slab, the length of the slab was 12 feet. In 705 we had wider slabs, like 12 feet, 13 feet slabs. So we saw transverse crack, longitudinal crack, corner cracks, and those cracks, number of cracks and the length of the cracks continued increasing throughout its life. So as of by the end of this year, 2019, like 55% slab cracked. So in terms of the fatigue crack, we probably crossed the design life. We are considering, let's say, 20% slab crack is the end of the life. If we consider that, then we probably crossed that. 805, which had narrower slabs, also seen both transverse, longitudinal, and corner cracks. And then those also increased, but these slab did not crack that much, which cells 705 had. So 28% slab cracked by October 2019 at 2.4 million ESALS. Now this slide shows kind of a comparison of the fatigue cracks and spalling. So we can see like the cell 239, which was 4-inch thick with a little weak base, shown maximum number of cracks so we did not include cell 139 in this comparison, because 139 really shown a different kind of failure, like the slab shattering, and then counting the cracks in those in that cell was difficult. And as we know that 75% of the slabs in that cell crack, so we did not consider cell 139 in this comparison. Now the comparison between 705 and 805 shows that 705, which had wider slabs, had more longitudinal cracks, and the the 805, which had narrower slab, had more transverse crack, but cell 705, as I said, it had 55%, and cell 825 had 28% slab cracked by October 2019. Now, in the other four cells, like 506 through 806, we only saw as a few cracks in cell 506, which didn't have fiber, but we saw a lot of spalling, and they remained we didn't see any increase in them in 2019. So as far as like fatigue crack quantification is concerned, now 506 through 806, that's the cells, those are the cells where we varied the fiber doses, but those slabs, in terms of the crack, they are performing really good. So we still actually could not quantify the fiber's contribution, or what doses fiber is good, or what residual strength ratio or residual strength would be good. So now this slide shows the percent slab crack versus ESALS, and these are for all the 8 cells. And you can see here now, if we consider 20% slab crack is, let's say, the design life or fatigue failure, if this is the criteria, now cell 239, it is pretty close, and the concrete overlays to unbonded overlays, they already crossed, and 4 other which were constructed on thicker base, they are still performing good in terms of crack. So these are some kind of the numbers I just came up with. 4-inch thick with 8 pound per cubic yard fiber, but one weak base. It's like 100,000 ESALS it took. Sorry about the spelling here. For to reach 20% slab crack, and then the 2 overlays that the wider slab one reached to 20% slab cracked at 400,000 ESALS, and the narrower one at 600,000 ESALS. So probably this particular research did not clearly show that if we can increase the slab size. The slab size variation was for 7 feet versus like 12 feet, 13 feet width. So this research says that maybe we cannot like double the width of the slabs if we use fibers. Maybe by 1 foot, 2 foot, or 3 foot, and which may not be a big deal, or may not be possible in construction. So we probably cannot double the size of the slab using fiber. So that is probably what we are seeing from the results of 2 thin unbonded concrete overlay. Now, joint performance. So joint performance was studied. We took FWD data. FWD test was periodically conducted, and then faulting was also measured. Now again, I did not include cell 139. Now in cell 239 we can see, but again we just cannot compare the fibers contribution in cell 239, but this we saw like the load transfer efficiency in the inner lane continue to drop. Okay, that means the concrete's interlocking or fiber contributions is decreasing with time. The inner lane is the lane where we MnROAD apply the load. Then outer lane actually is not loaded, so load transfer efficiency remained the same almost. Means like aggregate interlocking or the fibers are not getting fatigued. No load, no fatigue. So here the fatigue is influencing the load transfer. Now cell 705 and 805. So you can see, and we may be surprised looking at this data, the load transfer efficiency, uh, 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 is very low since the beginning. Now, what is the load transfer efficiency? Load transfer efficiency is the deflection under the unloaded slab divided by the deflection under the loaded slabs multiplied by 100, and we get the result in percentage. Now, load transfer efficiency has been low for both the cells. Okay, so keep this one in mind, and then we will see what kind of faulting we have seen in these two cells. Cell 506 through 806, where we varied the fibers, 506 no fiber to 806 with the highest fiber doses. You can see the 506, 606 and 706, the load transfer values varied, or you can say decreased right away after the construction, like right after the construction we got more, and then after whatever the values we have measured subsequently in in 7 other dates, we didn't get a very high amount of or even considerable amount of load transfer, as well below 60% or 70% what we need. Now 806, which had 11.7 pound per cubic yard of fiber, the load transfer efficiency has remained continuously high. So that means in these cells, fiber is really helping to keep the load transfer efficiency really high. Now look at the faulting here. So we had faulting for all the cells. Now cell 139 and 239, even though the cracks were like severe in 139 and 239, also 18% slab cracked, but in terms of the faulting data is not that bad. For 139, I would say like the slabs on both the approach and lip slab probably get equal amount of depression because of the weak base. So that's probably the reason we didn't see a lot of faulting there. 705 and 805 also did not show significant amount of the faulting, but like but when we saw the load transfer efficiency or even the deflection values in these two cells were really high. Now the deflection was high, load transfer efficiency was very low, but we did not see faulting. My understanding, and then there are a lot of experts in this room today, so we can think about it, but what I am thinking is the excessive deflection that we are getting or poor load transfer in these two cells we are getting is basically the it's probably the geosynthetic fabric that we used. So when you apply the load using the falling out deflectometer, so we are getting good amount of deflections. The fabric probably is just acting like a sponge. Okay, so that's the reason we are getting deflections more under the loaded side and very less on the unloaded side, which is giving very poor load transfer. So for this type of overlays where we have geofabric kind of bone breaker, I think load transfer efficiency may not be the best things to characterize the joint performance. So that's what it is showing right now. The faulting versus load transfer efficiency, they contradict each other for these two cells. Joint faulting for 506 through 806. Here we see like kind of clear picture how fiber is contributing. Let's look at the data we have for April 2019. You can see the plain concrete, which is the red one, is having higher amount of the faulting, and the green one is 806, which had the highest amount of the fiber, had less faulting. And then we put all those faulting results, average faulting results, together in this plot, and then like as the fiber is increased, faulting is decreasing. Also the faulting quantity is increasing. The next graph will show us like when faulting increases more. Now this graph compares faulting versus ESALS. These two graphs here are basically for our cell 139 and 239 on the low volume road track, and these are the 4 cells, 506 through 806. We did not include the overlay because that's completely different thing. So in this one, you can see like the faulting measured during the spring was significantly higher. See here, this was the spring 2019. This was the fall 2018. Right, so we are seeing a kind of a good jump during the spring, either because of the weak base during that time, but this is the data. So, and then compared to the spring and the fall, we are seeing marginal increase and sometimes no increase at all. This data here, it's showing almost the same below. Actually, these particular faulting results was lower than this. So excuse me. So now in one of our tasks, so we are using all the faulting results to develop faulting prediction models. We are also doing the same stuff for the fatigue cracking, but because of the fatigue cracking's data for 506 through 806, we did not see any good cracks, so we are still struggling with that because of not availability of the crack data for those cells where we varied the fiber. But we have analyze the faulting data and then try to create some models. Here we try to relate the measured faulting with respect to ESALS, slab thickness, residual strength, and base modulus. The base modulus we didn't have any test data, but we found out some other research works conducted on MnROAD where they have reported either resilient modulus or other parameters. So we used those to get K, and then we also got the K with respect to different seasons. So this is a kind of a typical faulting model, again not for exactly for the concrete overlay or thin concrete pavement on gravel base. These are for conventional concrete pavements. This model is by Dr. Zollinger and his group. So as you can see initially, like the faulting remains low, and then when layers get unbonded, pumping or kind of erosion takes place, the faulting start increasing. So we try to analyze our data in that kind of pattern. So now this is kind of now these graphs can look a little funny and complicated. So this particular one, you can see that these are the data. It's like this is the spring data. This was the spring, and hopefully we get more data now. So we try to model this shape, a little bit of more ambitious. So we try to model the shape, and then we got these lines are actually our models, and these all those circles are actually the field data. So here we the fault is in millimeters. So we had ESALS, slab thickness, residual strength of the concrete, fiber reinforced concrete, and modulus of subgrid reaction K. Now this K really helped us because K changes with the season. K will change with the season, so this kind of shape we could interestingly actually when we introduced the K, and then we found a good match with the good matching of the models with the data. Now this one is a little bit of simplified version, but in this one, if we do not consider the changes in the base modulus, let's say, or modulus of subgrid reaction, then we cannot actually capture the variation between the spring versus fall. So in this one, so this is probably kind of a model for long-term prediction, but the earlier graph actually can give us the more information how suddenly the faulting increases in the spring. So as I mentioned, we collected a lot of sensor. We had a lot of sensors installed, and then we collected all those data. So in these presentations, I'm not going to cover extensively. We are doing a lot of analysis on this data still. So this few slides just show basically very kind of key findings. So we had collected temperature data at different depth of the pavement, and we are collecting the data throughout the season. So this two graphs on the left just showing like how temperatures is varying with respect to the excuse me, the season, and then we calculate the temperature gradient. Now just an examples, the temperature gradient at 3 times what we have calculated here, X, Y, and Z are basically 3 times, like in high temperature and low temperature and kind of intermediate temperature. But in all those all the 3 times what in observations we found out, because the thickness of the slabs here is 3 to 5 or 6 inch, right? It's not like 12 inch. So the gradient is relatively linear. So you can see the gradient is relatively linear. Once a particular slab, and I do not know what is the reason, cell 239 1 sensitivity did not show, but if we take out these particular results, actually it's again probably linear. So we calculated the temperature gradient and then plotted their frequency, temperature gradient and frequency. So now these particular data help us understanding what would be the key temperature gradient, and also we compared the negative temperature gradient, positive temperature gradient. We saw the pavement experiences negative temperature gradient 60% of the times, means the top remain cold and the bottom is hotter. That kind of situation. In Minnesota, we collected strain using the vibrating versions of the environmental strain. So this green graph is basically the temperature, and all other graphs are strains, environmental strains collected by the different sensors. So so you can see the variation with respect to the temperature and season. So I'm not going into more details. We also have the strain by the wheel load. So we combine the environmental induced strain and the load induced strain, and then here in this slide you can see we compared, and then as anticipated you can see cell 139 has more strain than all other cells, and that's probably the reason why we have seen more cracks. Okay, so now these four cells, which are cells 506 through 806, you can see there the strain in these cells are relatively low. Okay, so and low, and I think it is around 40% of their modulus of rupture. So that's probably another reason why they are not cracking. We also collected joint movement. Again, I'm not going into more details, but you can see like some sensors are very active. They're like reflecting the slab movement, and some sensors remain really dormant. Okay, so which means the crack didn't deploy maybe. Okay, so this kind of data we are. So we also parallelly conducted laboratory investigations. Also we are doing finite element modeling. Laboratory investigations is completed, so and then which we will report in the final report of this project. This is kind of a little bit of additional thing that we did not have it in the proposal, but one of our graduate student has worked on that, so we'll include those in the final report. So what we try to do, as we know, the synthetic fiber that we use in pavement, a lot of researchers noted that they are prone to creep. So in this experiment, what we have done is we induced crack creep. So what is crack creep? So we actually cracked this beam. We kind of induced crack. Okay, this is a little bit of like all the cracks were not that wide initially. So this picture we chosen just to show the crack. So we use some flexural load to crack this beam at 18 hours after the construction. You can see we have this developed this facility where we could apply tension on them for 6 beams together. We can apply tension for the time how much you want. So we had, for this particular research, we had them for 10 days tension, and then this particular graph shows that the difference. So for example, we tested like 6 beams for one particular type of concrete. So in this one, so whatever the initial crack width, we had 40 mil crack width. We had 1 mil is 1,000 of an inch, so we had 40 mil, and then we had tension throughout this period. So you can see like the crack width kept increasing, and then we released the tension, but this crack did not go to its initial 40 mil. So we do not have load here, also we do not have load here. So what does that mean? That if we expand the crack, fiber gets kind of plastic elongation, or some fiber can pull out. So plastic elongation of the fiber or the fiber pull out, these two creates this crack creep. So now this crack creep influences the load transfer. So this is again a very simplified graph. We have like scattered data, so we just my student just plotted kind of a trend line. So the not creeped, we also had some beams which were not creeped. So you can see the load transfer efficiency were 20 to 30% or even more higher than those beams which were creeped. So this is another thing probably we need to look at. So this particular results or the finding tells that if fibers contributes in joint performance or load transfer, probably let's say in the first winter when the crack width is wide open, so fiber will contribute at that time. Now the contribution in the first winter or first spring will not be the same after the, let's say, fifth after 5 years. So because the fibers will repeatedly be creeped. So again, when we want to incorporate the fibers properties in the mechanistic design of, let's say, concrete overlay or thin concrete pavement, we probably need to consider this kind of creep of the fiber. Just like in asphalt, we consider aging of the asphalt. So this particular thing also should be considered, like aging of the fibers into the design. So in the conclusion, regarding the crack and spalling, so in cell 139, as we saw, 75% slab cracked. Probably 3-inch thick slab was too thin on a 6-inch gravel base. So now the structure was actually thin, so we actually could not, we probably cannot comment whether fiber was really doing anything in the cell 139. The structure was probably insufficient. So maybe next times we probably should either construct thicker cells, or we probably should construct the 3-inch layer on a relatively strong base. Then probably we can compare. So cell 239 performed better than 139. Wider panel in concrete overlays, wider panel, thin unbonded overlays experienced more longitudinal crack compared to the narrower panel ones, which experienced more transverse cracks. Compared to the pavement on gravel, they experienced significantly higher fatigue cracks, like cell 705 and 805 has more cracks than cells 606 through 806, which were constructed on the gravel base, or strong base relatively. So so all the 4 cells like 506 through 806 are performing well. Joint spalling was observed on cell 506. Let me go to the next slide because we probably don't have too much of time. Now on the faulting, as you saw, like cell 139, 239, even though they are damaged by fatigue, their faulting was less. And then fibers contribution was observed in 506 through 806. Cell 606, 706, 806 showed lower faulting than cell 506 with no fiber. Cell 706 and 806, even though it shown really low LTE, but faulting was less because of probably the geotextile. With respect to FWD, fibers contribution is observed in cells 506 through 806. Cell 806 showed higher LTE, and that was consistent. LTE for the cells 239 was also good, and this is, again, I'm just saying, cell 705 and 805 had low LTE, but they were doing good in terms of the voltage. So with that, I am done with my presentation, and then I'll be glad to take any questions.
All right, Manik, thank you for your presentation. This has been Worrell. I noticed 4 questions. One had to do with the operations of MnROAD, and right now we're kind of back working. We have our truck running. Jeff Brunner kind of answered your question, I think, Charles, but we basically lost 3 weeks of time where we're at home. We have people working safely out at MnROAD, keeping their safe distances. But again, our sensor data, environmental data, there was no effect on COVID-19 on that. The dynamic data, we've actually collected the data for our early spring and late spring testing. So really, we've been keeping up on that. The truck is running now, again, like I said. we've collected our early and late spring monitoring. So in some ways we did pretty well with this so far, and hopefully everyone's health around the country stays the same. But we're kind of back to collecting data, but we're not collecting data holding hands right now. Manik, there is a couple questions. Tom Burnham started it out, and I don't know if you want to read it, but I can read it real quick.
Yeah, so I'm just like looking at Tom's question. If you allow me,
go ahead.
I can read it.
We only have 5 minutes, so keep it quick
so
if you can.
Tom's question is basically, do you have any opinion on the rate of deterioration of the cracks due to fiber content? I think right now no, because cell 506 through 806, where we varied the fibers, that did not give us many cracks. Only 506 had 3 cracks which did not have any fiber. Other cell 606, 706, 826, where we had 3 different doses of the fiber, we did not see any cracks. So I think I probably cannot comment on that one right now.
Okay, and then Bernard had a question that was talking about should there not be the radius of relative stiffness in the faulting models independent variables? Did you see that question?
Yeah, that's a very good point. So we yeah, we definitely can try on that. Thanks, Bernard. Very, very important question. So we included K, so radius of relative stiffness, which is function of modulus of elasticity of the concrete, then thickness of the slab, and modulus of subgrade reaction, and Poisson's ratio of the concrete. So the modulus of elasticity and Poisson's ratio do not change too much if we use the fiber, right? So the fiber that we use now, thickness, modulus of elasticity, and Poisson's ratio. So these 3 factors are relatively dormant with respect to the fiber's content if we use synthetic fiber. So I don't think it will be a significant factor, but we can definitely investigate. So what was changing is the K actually, and then we saw this K was influencing. So we did little bit of statistical kind of analysis, which factors are significant or not significant, but we did not definitely have the radius of relative stiffness. We will do that one, and then I'll get back to you, Bernard.
Okay, thanks, Manik. And then Raul asked a question. Do you see there near the bottom of the questions? Try not to repeat it exactly, but do you see that, Manik? It's during the presentation plot showing faulting and fiber content indicate a positive effect of fibers. However, can you please clarify each of those cells presented in a plot have the same foundation? Same. And
yeah, so for 506 through 806, we know it is same foundation. So now if the foundation varies, you know, with little drainage issue in one particular cell, so with respect to the other, I cannot comment on that, but cell 506 through 806 were technically on the same foundation. Cell 139, 239 were on the same foundation. Cell 705 and 805 were on the same foundation.
Okay. And then Bernard had a follow-up question. I'm not sure if that was related to the other one, but crack width plotted and modeled in time series will be interesting to see. Your crack creep concept, if a significant finding might be, is a significant finding, he might have meant.
Thank you,
Any last comment on that? And we have one more from Deepak.
Was there issue? So Ben, you want me to look at the last one?
Yeah.
Was there issue in mixing high amount of the fiber? Well, this is a really construction question. So I was present during the construction of cell 806, which had almost 12 pounds of fiber. The mixing was not a very issue, but I saw like the very first couple of slab had the concrete was, the workability was a little bit of problem, so they had a little bit of finishing problem. The workability dropped because of the 12 pound of fiber. So this is kind of the logic here. So if you increase the more fibers, the workability drops. So workability was the issue, but as I said, it was only observed in the first couple of slabs, and then after that I think they changed the workability a bit, and then it was not a big issue. As far as fiber uniformity, like the homogeneitiness or whatever you said, the mixing, I did not see any kind of fiber bowling with the fiber that was used in those cells.
Okay, well, we're kind of running out of time now, but Deepak, I think related to this is it seems like the fibers over the years have gotten a lot easier to mix into the concrete. There's been less of an issue with that, but Tom Burnham or Bernard Isawai would be great resources for that question, and maybe they can bounce you an email later. Also, if I may add, Lauren Dow added a survey. If you would all click on that and give us your feedback, we'd really appreciate it. And again, looking forward to having our, I want to thank Manik for his presentation. You did a great job, and hope to see you all next week and also during the kind of our research workshop presentation that'll be coming up, and you'll see more information on that later. So with that, thank you.
I'm saving these questions, and then if I had not got a chance to answer all of you, I'll separately email you.
That's perfect. Thank you very much.
Thank you. Thank you very much.
Everyone have a good day.
Good day.